A quantum computer doesn't look or act at all like the computers that we use every day. It relies on different laws of physics to run calculations at super fast speeds. Tonight, Google is revealing a breakthrough in the technology that it says could ultimately lead to the discovery of new kinds of medicine or help grow our food more efficiently. With a rare look inside Google's quantum computing lab.
A machine that cannot speak a single word may have just handed physicists their most unsettling answer in a century. Not a sentence. Not a proof. A pattern. One that showed up in exactly the place nobody expected to find it. And it left a room full of some of the most rigorous scientists on Earth sitting in silence, unsure of what they were looking at. To understand why that silence mattered, you have to understand what was actually sitting in that lab. In December of 2024, Google's quantum AI team announced a chip called Willow, and unlike almost every headline before it, this one didn't fade after a news cycle. Willow is built from qubits, not the bits your phone or laptop runs on. A normal bit is either a 0 or a 1, a single fixed answer locked in place. A qubit refuses that choice. Through a property called superposition, it can hold 0 and 1 at once. A genuine blend of possibilities that only collapses into a definite value the instant it's measured. Pair that with entanglement, the phenomenon Einstein spent years trying to dismantle because it seemed to let two particles respond to each other instantly across any distance, and you get a system that doesn't calculate the way your laptop does. It doesn't check possibilities one at a time. It lets huge numbers of possibilities interfere with each other, the way overlapping waves cancel out the wrong answers and reinforce the right one, until a solution emerges that no classical machine, no matter how large, could reach in any reasonable amount of time. Google gave Willow a single benchmark task, a problem specifically designed to be brutal for ordinary computers. Willow finished it in under 5 minutes. Google reported that the same task, handed to one of the world's fastest existing supercomputers, would take roughly 10 septillion years. A number so far past ordinary comprehension that comparisons to the age of the universe actually undersell it. The universe itself, at around 13.8 billion years old, is a rounding error next to that figure. This wasn't a marketing stunt dressed up as science. The benchmark was published, peer-reviewed, and picked apart by outside physicists specifically because that is how quantum supremacy claims get taken seriously. Nobody serious in the field disputes that something happened in that chip that classical computation, run the ordinary way, simply cannot replicate. But the number that actually shook people wasn't the speed. It was something quieter, buried in the mathematics of what Willow was doing. Physicists working alongside Hartmut Neven, who leads Google's quantum AI division, found that the sheer volume of computation the chip appeared to be performing seemed to exceed what could plausibly be happening within the physical bounds of a single universe. There seemed to be more calculation taking place than there was room for it to occur in. And Neven, standing in front of a result that looked like it was overflowing the edges of reality, said the thing that traveled through the field like a hairline crack spreading across ice, that the computation might be happening across many parallel branches of reality at once, each one contributing a sliver of the answer, all of them handing their piece back into the one branch we happen to be standing in. That is not a phrase Neven invented casually. It leans on a framework in physics that has existed since 1957, when the physicist Hugh Everett proposed what's now called the many worlds interpretation of quantum mechanics. Everett's idea, later championed forcefully by the Oxford physicist David Deutsch, one of the founding theorists of quantum computing itself, is that every time a quantum event resolves, the universe doesn't pick a single outcome. It splits. Every possible outcome plays out, each in its own branch, invisible to all the others, all of them equally real. Deutsch has gone further than most physicists are willing to, arguing that quantum computers are themselves the strongest evidence we have that those other branches exist. His reasoning is simple and, if you sit with it, genuinely disorienting. When a machine performs a calculation that would require more computational steps than there are atoms in the observable universe, where exactly did that computation happen? Deutsch's answer is that it happened elsewhere, in branches we cannot see, and the machine simply collected the result. This is where the story stops being a story about faster chips and becomes something else entirely, because once physicists started looking closely at what made Willow work, they noticed the same kinds of structures showing up again and again in places that had nothing obviously to do with each other. Take the E8 lattice, an 8-dimensional mathematical structure with 240 points of perfect symmetry, so intricate that mapping it fully once required a dedicated research team and a supercomputer running for years. Nobody built E8 to be elegant. It fell out of pure mathematics on its own, and physicists chasing unified theories of particle physics, including work associated with the physicist Garrett Leasy, keep finding that the deepest attempts to describe reality's fundamental forces want to fold themselves into that exact shape. Then there are fractals, patterns that repeat at every scale, from the branching of blood vessels to the spiral structure of galaxies spanning 100,000 light-years. Physicists have a formal name for the mathematics behind this self-similarity. Renormalization, the study of how physical laws shift as you zoom in and out across different scales of reality. What keeps surfacing is that the universe behaves as though the same underlying rule is being applied over and over, from the smallest measurable distance to the largest visible structure. It didn't have to work that way. Nothing forces a coherent universe to rhyme with itself at every level. And yet it does. The third pattern is the one that actually rattled people, because it didn't just look beautiful, it looked engineered. In 1995, the physicist Peter Shor was working on a problem most of the field considered unsolvable. Quantum information is famously fragile, and the smallest disturbance destroys it. Shor proved you could encode a quantum state so cleverly that even if pieces of it were disrupted, the original information could be recovered intact. He had invented quantum error correction, and in doing so, he had unknowingly described something that would show up again decades later in the deep architecture of the cosmos itself. Error correction isn't the kind of thing you expect nature to produce for free. In every context we build it ourselves. It's a defensive technology, something engineers add deliberately because they anticipate failure in advance. Google's landmark 2024 result, published in the journal Nature, showed that as Willow's qubit count increases, its error rate doesn't rise, it falls. The system becomes more stable as it scales, the exact opposite of how fragile systems are supposed to behave. Here's where it gets stranger. Physicist John Preskill at Caltech, alongside researchers including Ahmed Al-Mhairi, Shi Dong, and Daniel Harlow, examined the mathematical structure underlying the holographic principle, the idea, well supported in theoretical physics, that all the information contained within a region of space can be represented on that region's boundary, like a cosmic hologram. Their work showed that this holographic structure follows the mathematics of a quantum error-correcting code with remarkable precision. That idea didn't come from quantum computing at all. It emerged from decades of work on black holes and the puzzle of what happens to information that falls past an event horizon. And the answer that kept surfacing was that reality seems to store its information the way a careful engineer would, redundantly, spread across a boundary, encoded so that no single point of failure can erase it. The same mathematical family that keeps Willow's fragile qubits alive appears to be the same family holding the structure of spacetime together. None of this proves a designer exists. No physicist working on these problems would tell you it does, and anyone claiming a quantum chip printed out a signed confession from the creator of the cosmos is selling you something. What's actually happening is quieter and, in its own way, more unsettling than a simple answer would be. The universe keeps returning numbers that look chosen rather than random. The cosmological constant, the energy embedded in empty space, sits at a value fine-tuned to roughly 1 part in 10 to the 120th power, a precision so extreme that ordinary metaphors about needles in haystacks fail to capture it. There's a smallest meaningful unit of length, the Planck length, below which the concept of distance stops making sense, as though space itself has a finite resolution. There's a hard ceiling on how fast anything can move, the speed of light, in the same way a processor has a hard ceiling on how fast it can move information. And there's the case that still makes physicists uneasy. In the 1950s, the astronomer Fred Hoyle realized that carbon, the element essential to all known life, could only form inside dying stars if carbon nuclei possessed a very specific, previously undiscovered energy resonance. He predicted it had to exist for the simple reason that we exist to ask the question. Researchers went looking. It was there, sitting exactly where the math demanded. Hoyle, who held no religious motivation whatsoever, later remarked that the universe looked like a deliberately arranged system. There is a way out of this puzzle, and intellectual honesty requires including it. If there isn't one universe but countless ones, each with different physical constants set essentially at random, then fine-tuning stops looking miraculous. Most of those universes would be sterile and dead, incapable of forming atoms or stars, let alone life, and naturally no one is around in the dead ones to be surprised by their emptiness. We simply find ourselves in one of the rare universes that works, because we couldn't exist anywhere else. It's an elegant argument, and many serious physicists rely on it. But it doesn't eliminate the strangeness so much as relocate it, trading one improbably tuned universe for an almost unimaginable number of untuned ones and the vast unexplained machinery required to generate them all. This is roughly where the conversation collides with an idea that has moved from philosophy departments into serious physics conferences over the last 2 decades, the simulation argument. In 2003, the Oxford philosopher Nick Bostrom published a paper laying out 3 possibilities, arguing that at least one of them must be true. Either civilizations capable of building detailed simulations of reality almost always destroy themselves before reaching that capability, or they reach it and almost universally choose never to run such simulations, or we are very likely living inside one right now. The logic is uncomfortable once you actually follow it through. If advanced civilizations do run many simulations of conscious minds, simulated observers would vastly outnumber the rare original, non-simulated ones, meaning any randomly selected conscious being, including you, listening to this right now, would statistically be far more likely to be one of the simulated majority. Bostrom's paper has been cited thousands of times, and physicists have started asking whether a simulated universe would leave any detectable trace, some faint graininess at the smallest possible scales of space, the way a video game's world is ultimately built from a fixed grid of pixels. No one has found such a signal. But the fact that researchers are now designing real experiments to search for it tells you how far this question has traveled from speculation toward something resembling testable science. The physicist Max Tegmark has argued something adjacent to this for years with his mathematical universe hypothesis. The idea that reality isn't merely described by mathematics but is, in some literal sense, made of it all the way down. So we're left with 3 honest ways to read everything Willow's results have surfaced. The first stays closest to established physics. The universe is fundamentally mathematical, and the patterns keep appearing because that's simply what mathematics does when it's consistent and self-referential across scales, real, elegant, but requiring no author. The second is bolder. If reality behaves like a quantum error correcting code because it functions as one, then the fine-tuning of the constants is a parameter someone set, and Willow, operating at the deepest layer physics can currently reach, is inadvertently probing the edge of that architecture. The third answer, and the one a growing number of physicists find hardest to dismiss, is simply that we don't know yet. The patterns are real. The fine-tuning is real. The apparent overflow of computation beyond any single universe's capacity is real. But whether any of it points toward mathematics, toward code, or toward something science doesn't yet have language for sits just past the current edge of what we can measure. What's worth noticing is that 2 of those 3 answers, eternal mathematics and deliberate simulation, sound like polar opposites, a cold accident on one side and an intentional creation on the other, and yet they quietly agree on the deepest point. Underneath everything visible, reality is built from structure, from information, from pattern. They only disagree about whether anyone put it there. That's a smaller disagreement than it first appears, because it means the real debate is no longer about whether the universe has a hidden order. We can already see the order. The only argument left is about where it came from. Every time humanity has built a new instrument and pointed it at something previously unreachable, the answer has come back stranger than expected, not smaller. When early microscopes revealed entire living worlds inside a single drop of pond water, reality didn't shrink to fit our expectations, it expanded past them. Willow is that same kind of instrument, aimed not at the very small or the very large, but at the very deep, at the layer where physics starts to look like information asking a question about itself. It's still a prototype. Google's own roadmap points toward machines that will make Willow look primitive by comparison, and nobody currently working in the field knows exactly what those machines will eventually surface. So maybe the honest ending here isn't a verdict. It's an invitation to sit inside the uncertainty a little longer than feels comfortable, to let the patterns unsettle you without rushing to file them under either miracle or accident. The universe didn't hand us a sentence. It handed us a shape, and shapes take patience to read. If there's a builder behind it, we haven't found their signature yet. If there isn't, the elegance still deserves the same attention. Either way, something in these results asks us to keep looking rather than to look away, and that, more than any single answer, might be the truest thing this entire moment has given us.